is a fresh new series of videos on the course of linear algebra. Thanks to all of you who have responded to my poll and have said yes, a course on linear algebra is very helpful. A huge note of thanks, gratitude for answering to my poll, and that is the reason it motivated me to create a fresh new course on linear algebra. I think that I can live up to your expectations and deliver at my best. Again, a huge thanks to all of you for responding to my poll. This course will contain everything that I would like to express and clear the concepts of linear algebra apart into vectors and everything else, so that the learning of linear algebra would be useful, the exercise, the concepts, as well as learning of quantum mechanics will be very helpful to you, because as I have already started a series of videos on complex numbers and linear algebra, this would be a very exhaustive course containing only and only all the concepts and problems of linear algebra. My name is Shaunak and you are watching this video on my channel Physics for Students, a fresh new course, and welcome to this new episode of linear algebra. So first let us look at what are the areas that we are covering today. So the topics that we are covering is that first we need to understand what is the need of the subject, that what is linear algebra. Why linear algebra do we use, and at all is it helpful or not? A little bit introduction on vectors. Vectors as linear combination, certain examples, what is a null vector, and certain operations like addition, multiplication, etc. So this is the first lesson. So I will be going through the basics, but I will give you a lot of good insights and deep understanding of the concept of linear algebra. So first, let us understand what exactly is linear algebra. We do a lot of mathematics, we pass in the examination doing good scores, but at sometimes we feel that we really do not know what is linear algebra is all about. So as you see that linear algebra actually deals with certain areas and many difficult problems can be handled easily once relevant information is organized in a certain way. Now you see that most of the high profile use of linear algebra was in the creation of Google. So their original ranking algorithm, which has since surely become far more complicated, used a lot of linear algebra to rank which web pages would show first, etc. More generally, any time you want to analyze a random walk in a network, you're likely to need some linear algebra. Linear algebra is also used in most sciences and fields of engineering because it allows modeling of many natural phenomena and computing efficiently with such models. So the basic idea of linear algebra is that there is a huge amount of information in front of you. The information can be in terms of population, data science, anything, and linear algebra actually helps to organize those information and understand in a better way, thereby helping us to process the data and get certain results. Now when I talk of information, I would like to show certain examples that what do we mean by information and how linear algebra actually helps in. Okay, how do we organize information? Now see, functions of certain variables are often presented in one line, such as this: f of x of y equal to 3x plus 5y. But let us think it carefully. Now you see, which is in the left hand side, this is the function of several variables, but this part which is on the left hand side of the equation, what actually it is doing. Functions and equations are different mathematical objects, so why is the equal sign necessary? So what is actually this doing? Now if someone says, consider the function of two variables 7 beta minus 13b, well, we do not have quite a lot of information and we need to determine the relationship between the inputs. Now for example, you own a company, three companies. One is Ganymede, Andrestia and Neptune. Well, the first question to you is that, can you tell me what are actually those? Obviously these are not the name of the companies, fictitious, but what are actually Ganymede, Andrestia and Neptune? You already know. So first to a question to you. Okay, so suppose you own the stock of these three companies, and let us assume the value V for your stock portfolio as a function of the number of your share, and I write something as this. So 24 SG, 80 SA and 35 SN. So this is basically the number of shares. So SG, certain the shares of Ganymede, share of Andrestia, and share of Neptune. Now what about this one? If I write, I mean to say, what is this? Yes, yeah, I'm thinking over there. So we got the number of shares of 3 companies and we write it in this way, V123. What actually it means? So we turn the page. It might mean 1 share of Ganymede, 1 share, 2 shares of G, and 3 shares of A. Is it so? Or 1 share of N, or 2 shares of G, or 3 shares of A. So you see, what I'm trying to tell you right at the beginning is that these information, I'm not taking mathematics right now, I'm taking stock market, for example, share, something related to finance. I'm trying to make you understand that what actually do this means. Do we multiply the first number of the input by 24 or 35? No one has specified the order of the variables, right? So we are still confused. We do not know how to calculate an output associated with a point. Now, what we do is that, yes, there are no one which is specified. Now, if we mention V by 24, 80, and 35, and then we write this one, right? So what it happens is that 24 obviously relates to 1, 80 relates to 2, and 35 relates to 3, and it gives the result something as this. Now, why it has happened? Because we chose the order of this one as this, GAN. And now what we can do is that, because GAN are the number of stocks, etc. So we have calculated in this fashion. And yes, from here we can say that this so looks something like this. Now you see on the left hand side, the V123 looks similar to this person who is saying, yay, I have done it. So that means the number that has been organized is now showing a sense. So this is how actually in industry and other areas, linear algebra helps. That when we get random numbers, stock markets, population, any kind of a data, we really do not know how to do that and how to share. So this is the way in which we do. Now what about that we change the order of those information and we write 35, 80 and 24, not like the earlier. And thus we write this is as B prime. Now see, B and B prime, these are on the columns of just symbols. Just remind that how to interpret the column of numbers, but this distinction will be critical as we see. So to remind that 35 relates to 1 and 80 relates to 2 and 24 relates to 3, and ultimately it gives a different number, that is 264, but the earlier one was 334, right? So we choose, why? Because we choose the order as NAG, but the order was earlier order was GAN. And so the inputs are now interpreted as SN, SA and SG, whereas earlier was SG, SA and SN, right? So what is happening is there that V here assigns a completely different numbers to the same column of numbers which different subscripts. And as you see, the values are something different. So I just wanted to make clear right at the beginning that these are the ways to interpret data. Interpret data in terms of industry, scientific researches, whatever be the data, linear algebra actually helps in to do that. Now there are 6 different ways of these 3 companies to assign those data. Each way will give different notation for the same function V, but in a different way of assigning numbers columns. So this is critical to make clear which ordering is used if the reader is to understand what is written, and this is how information can be arranged. So this is the first way to understand that how information is being arranged, and you see changing the order totally changes the output results. That means that is how linear algebra interprets those information. Okay, so we pretty know what are vectors. So I'm possibly I won't go deep into vectors, because once you're learning linear algebra, it is quite sure that you know vectors. But just a few points. Some of the examples of things can be added. So it can be numbers both 3 and 5 which can be added. It can be a 3 vectors, something like this. It can be also polynomial, where if p of x equals to this and q of x equals to this, then there's sum. This one is a new polynomial. So I'm just giving you examples that what actually are vectors. It can be numbers, simple. It can be 3 vectors which are arranged in matrices, and it can also be a polynomial. It can also be a power series, something like this. If f of x is 1 plus and it carries on, and then g of x carries on, then f of x plus g of x is also a new power series. It can also be a function, like if f of x is exponential, then the sum is equals to 2 cos hx, right? So this is also number. So there are clearly different kinds of vectors, but remember that this is a wrong concept that generally stack of numbers are only vectors. No, stack of numbers are not the only things and vectors, as these examples show. So this is just to let you know that how vectors really look like, and you understand that vectors of different kind of things cannot be added. So that is why I've given a simple example of different people standing together. What possibly could it mean to if we have this kind of a number, right? So you should think of all 5 kinds of vectors. This one, the numbers, the 3 vectors, the polynomials, the power series, and the functions. So I mean to say, because vectors of different kinds cannot be added, these are all different. So these you should start thinking of vectors, and you should not add vectors that are not of the same kind. On the other hand, any 2 things of the same kind, you see same type of people holding their hands, can be added, and any 2 things of the same kind can be added. This is the reason we should start thinking all of these objects as vectors, right? So this is a kind of a nice example which demonstrates vectors. I used a lot of pictures just to make the illustrations more correct. Now when adding the same vector over and over again, x plus x, x plus x plus x, and so on, we can write something as this: 2x, 3x, 4x. Now for example, we can also use this one, 4, 1, 1, 1 equals to this, and it goes and gives the result 4, 4, 0. So defining 4x equal to x plus s, so you see this is linear. It goes in this direction, this goes in this direction, and this goes in this direction. So we will explore more about what do we mean by linear, but let us understand that these are going quite straight, right? So you see that x plus 4 times x, these works okay. I mean to say, these are fine with integers, but it does not help to work with a sense of this kind of figure, 1 upon 3x. So for the different type of vectors that we have seen, we can probably guess how to multiply a vector by a scalar. So for example, we can do this, right? This is done by multiplication, sorry. So, and another vector, a very special kind of a vector, can be produced from any vector of any kind by a scalar multiplying any vector by the number 0. And this is called zero vector. The concept of zero vector is extremely important, and we will just find out what is zero vector in the next part of our video. So we get something like this, the 0 number, and then we get the 0 function, then we get a 0, 3 vector, and then we get a 0 polynomial, and we get this 0 power series. So vectors are things you can add and scalar multiply. So it just multiplies and gives the result of this kind. So I think this is very important, and this concept is clear. So what are the examples of different vectors? Numbers we have already seen, n vectors and second order polynomials are also there, power series, function with certain domain. These are all different types of vectors. So before we proceed and understand, it is important that we understand vectors in its true sense. Okay. So we move up to the next part of our video, which is extremely important, which is called vectors and linear combinations. Now, what do I mean by this? Now, see, the heart of linear algebra, I would say the core of linear algebra, are in 2 operations, and these are both with vectors. So we add vectors, for example, v plus w. We can multiply them by some number, for example, c and d, and get cv and dw, right? Combining these 2 operations gives the linear combination. We can multiply and gives a linear combination cv plus dw, right? So this is the linear combination. Combining this means combining the addition and the multiplication. So we get a linear combination over here, and we also get a linear combination over here, and combination with c equals to 1 and d equals to 1, right? So this is what we call the linear combination. Okay, we move further. So linear combinations are very important in this subject. So here it is, linear combination, the very heart of linear algebra. Now sometimes we want a particular combination, the specific choice of C equals to 2 and D equals to 1, that C equals to 2, D equals to 1, that produce something like CV plus DW equals to 4 or 5. So all other times we want all combinations of V and W coming from C and D. Now you see the vector, this CV, if I say it lies along a line, this is important conceptual. Now when W is not on that line, the combination of CV plus DW fills what is called the whole two-dimensional plane. Now I have to say and I have to pronounce the word two-dimensional plane, because as we will see that once we move into special theory of relativity, quantum mechanics, etc., linear algebra actually allows higher dimensional plane. And once we go up the ladder, you will see that how linear algebra is actually helping us to understand and do computation in higher dimensional plane. So that is why we say that when W is not on that line, the combination produces a whole two-dimensional plane, right? So starting from 4 vectors, which is right on the front of your screen, U, V, W, and Z in 4-dimensional space, their combinations produce something like this. So I'm multiplying C with D, with E, and D, right? So that is how this should be F anyway. C plus D plus E plus F. So what happens is that I would say that these boldface are basically vectors. I could have used the arrow on the top, but anyway, this looks very neat, right? And they're likely to fill the space of this 4-dimension, but not always. Remember, this is not always true. This is not always true, but in some cases, the 4 vectors, obviously, as we see in special theory of relativity and further, it actually clears up the fills up the 4 plane, but not actually. The vectors and the combinations could even lie on a single line. Okay, so now we come a little bit to what is called a vector operation and zero vectors. Now here one thing very fundamental is important, that you cannot add an apple to an orange. This is not being done. So in a strange way, this is the reason that for vectors we have 2 separate numbers, say for example v1 and v2, and their pair produce a 2-dimensional vector which is a column vector. Even if we do not add v1 and v2, we do add vectors, right? So we can just write something as this, which is a column vector. So we write V as column, not as row, remember. The main point is to have a single letter V, which is in boldface italic with this pair. Okay. So even if we have seen that even if we do not write v1 and v2, we add vectors, and this one is the first component, this is the second component, and this is called what is the column vector. So we can add v1, v2, w equals to w1, w2. Remember, w is written in bold, so it is a vector, and it adds up to v plus w, it adds up to v1 plus w1 and v2 plus w2. Okay. So you see that we want to add apples to apples, right? So subtraction of vector follows the same idea. We cannot add apples to oranges, so we add to apples. So the components of v minus w are v1 minus w1 and v2 minus w2, quite obvious. The other basic operation is something which is called a scalar multiplication. So vectors can be multiplied 2 or by minus 1 or by any number, for example c. Now there are 2 ways to add a double vector. One way is to add v plus v. This one, this is a scalar. So one is amplifying v plus v or multiplying each component obviously by 2. So here is a nice example of scalar multiplication where I have added twice v and then it is this. So the components of CV and CV1 and CV2, the number, this is called a scalar. Now this is something which is also called a concept which is called a zero vector, and I will just explain you what actually it is. So we define a vector as an object which has a length and a direction. However, there is one important exception to vectors having a direction, the zero vector, this one, which is denoted by 0. That is the unique vector having length as 0. With no length, the zero vector is not pointing to any particular direction. It is an undefined direction. So it is denoted either by boldface 0 or 0 on the top. So 0 plus a, and this one, this gives a 2-dimension, and this gives a 3-dimension. Now what is something very interesting is that this is 3 dimension. Remember that this 0 is not the same as number 0, right? These are just components of 0, right? Yeah, wow, that's a news. And the vector 0 has components as 0, 0. So it is actually not the it is not the number which yields to 0, although it looks like, but the vector has 0 as components as 0, 0. It's very fundamental, and we will see that how this component, once we explore further into the videos, I mean to say in the next video, we will see the importance of 0 vector. Okay, so you see the ordering of addition doesn't really makes any difference. I mean to say this and this, these are more or less the same. So that is how it really makes any difference. So combining addition with scalar multiplication is what is called a linear combination, and yes, the sum of CV and DW provides a kind of a linear combination of V and W, and that is what is the basic definition of 0 vector. I mean to say, sorry, the linear combination. Okay, so let us quickly see what is the summary of our first lesson that we have learned. So we have learned what is linear algebra, how linear algebra really helps in storing information, because we have seen that once we alter and change the way information has been stored, the entire scenario changes. So we have seen that changing orders changes informations. We have seen vector and vector operations. We also seen that vectors as linear combinations, and most importantly, what is a 0 vector. So that summarizes today's lesson, and in the next video we are going to look into vectors in 3 dimensions, lengths and dot products, lengths and unit vectors, and the angle between vectors. So this is the first lesson. I hope I can meet up to your expectation. Please do let me know how do you feel and how the series would be progressing in the comment section. Please do subscribe and click on the bell icon and click on all to get all the notification from Physics for Students. Put up your comments so that I can really know what are the areas that I can improve and go further. Again, a big note of thanks for responding to my poll, and I will continue this series on linear algebra and the other series that are continuing in my channel Physics for Students. Thank you very much and wish you a great day ahead. Goodbye.
Thank you for watching this video. We appreciate your time and patience. If you want to connect with us and provide further feedback, comment or suggestions, please email us at contact.physicsforstudents@gmail.com. You can also follow us on Facebook, Instagram and LinkedIn. See you soon in the next video.